Today we are going to move into a new topic, which is skin-stringer idealization. So as this is actually a step towards analyzing aircraft component analysis of aircraft components. Okay, so what did we do till now? So till now we had actually dealt only with beam, thin wall beam to be very specific. Okay, so what we have done is that we have taken a beam, we have seen or we have analyzed the beam due to torsion, then bending, and then due to shear forces. So we are now in a position, if we are given a thin wall beam, we can under any load or any combination of load, we can find out the stresses, which could be normal stress or it could be shear stress, and also we can find out the maximum value of these stresses. And the motivation is that we will probably check whether this maximum value is below the ultimate strength or allowable strength, including the factor of safety, and see that the beam is not going to fail because the maximum stress is crossing the allowable stress. So that was one major part of the course. So now we are going to move or extend what we have understood in analyzing, in going a step forward and trying to analyze aircraft components like fuselage, wing, tail surfaces, and other components. Okay, so so the skin-stringer idealization that I am going to talk about today is a step towards analyzing such structures. So the picture that I have drawn is the schematic of say a wing surface, okay, a wing cross section, and the blue colored this blue colored things are basically the stringers, or to say any longitudinal member. It could be longerons or spars. Okay, so any longitudinal members. And the this is basically the skin of the wing. So what so this if you remember what we have talked in our first few lectures, is that this is what an aircraft cross section of an aircraft component looked like. It has a thin skin which is stiffened by longitudinal members and also transverse members like ribs and bulkhead, which I have not drawn. Right? So I have just shown the cross section of a aircraft component, which shows the skin and the longitudinal members, which could be stringers, which could be spars, longerons, anything. Okay, so what we have done till far is that we have been able to, so these stringers are beam-like structures. Okay, and these stringers, if you remember, or the longitudinal members, if you remember, are the primary structural component which carries the or withstand the bending load, which gives rise to normal stresses that you have studied earlier. Now we know how to analyze this stringers or this thin wall beam because of bending and the direct stress that develops in the beam. So that part is done. Okay, and we also know that the skin is going to take the shear stresses, okay, because of torsion and the shear forces. So skin actually bears the shear stresses due to torsion or shear force. Okay, so that also we know. So this part also we know. If I have a thin wall structures like this with multiple cells, we know how to find out the shear stress distribution or shear flow that happens due to applied torsion or shear forces. Okay, so individually we know how to analyze the stringers. Okay, we know how to analyze the entire skin cross section because of torsion and shear forces. Now our job is to combine these two and to analyze the entire component. Now there comes the point. So as you might be aware, with this high performance computing becoming so easily available, like all these GPU cars and all, so I mean, the entire numerical analysis of a component is very easy these days, right? You can just take a whole wing structure, do a finite element analysis, do parallel processing, or run it in any high performance computer, and you can get the stress analysis for all possible load at every point on the wing. Okay, that's a very easy task. But then why did we go through this entire rigorous analysis of stresses because of all kinds of load? That, for number one, is that the numerical analysis is only going to give you numbers, okay, which will represent the stress. But to make meaning out of those numbers that represent the stresses or deflections or whatever, you should have an understanding of the physical behavior of this component or mechanics of this component. That's where one motivation of this analysis that we have done till far. Okay. The second motivation is that sometimes, I mean, however cheap this high performance computing might be, you cannot afford to do an entire finite element simulation of the entire aircraft at the design level. Because at design level, you might be able to appreciate, though you have not done any design code, there would be several iterations, right? You will come up with the shape of a wing, which you will see that it is not acceptable. Then you will refine the design of the beam and then again redesign. So at the design level of a component of the aircraft, there are several iterations, okay, before you pinpoint a particular design, a particular configuration. That I guess all of you all will be able to appreciate. Not only with aircraft component, with any with a machine, with a building, with a civil construction, there are lots of iteration at the design stage. Now, at this level of the design stage, it is not viable even with high performance computing, and it is not advisable to do a full scale numerical stress analysis of an aircraft component, and thereby at every step of that, at every iteration of this design process. Okay, so what we need at that point is that a very easy and quick method to get some ballpark figure of the stresses, okay, so that it helps us to go through those iterations of the design stage. Okay, so you have to remember that this easy calculation that we need at this stage of design might not be very good in accuracy. You might not get a very like 95% accuracy in the stress. It might give you something around 80 to 85%, even 75% of accuracy, but that's also good enough at the design stage, because you just want to have a ballpark figure. Okay, and you don't need to have the accurate value of the stresses. So because of these two uh, objectives or motivation, these two objectives which motivates the whole analysis that we are going to talk about at this point. Okay, so you again, the other point that I want to say now is that you probably will be able to appreciate that analyzing this whole wing structure with the skin, this two-celled wing structure with the skin, with all the stringers acting, okay, it's a very complicated task. Okay, it's a very cumbersome calculation that you have to do, so which you always wish to be quicker and easier at the design stage. So there comes the Skin-Stringer analysis, idealization, where you kind of approximate this configuration, this the actual, so this is your actual structure. Okay, so you would like to approximate this actual structure into an approximated structure, approximated or idealized structure, okay, which will be much easier to analyze. Okay, now let me talk about, so this is what you are doing. So, and this entire thing you are doing for easy calculations with certain trade-off in accuracy. But you don't mind, because these are not your final calculations, right? These are just at the design stage. So this is happening during design iterations. Okay, now let us talk about how do you approximate that the figure that I have drawn. How did I get this figure from? So let me call this as figure 1 and this as figure 2. How do I get figure 2 from figure 1, and what does figure 2 represent? So let me so now let us go one by one. So this whole structure is going to experience bending load. Okay, and this bending load is going to produce direct stresses. Now you know that the longitudinal components, okay, as shown by the blue figures, are the major, I mean, withstand the major part of this direct stresses. But apart from the stringers taking major part of the direct stresses, part of the skin also takes certain part of the direct stresses. Okay, so this blue colored lines, this blue colored figure takes major part of direct stresses. Okay, but this also takes some direct stresses. Take as in withstand direct stresses. Okay, so now what I do is that I replace this stringers. Okay, I replace this stringers by a concentrated, so this is concentrated concentrated area at the location of the stringer. So wherever I have a stringer, I have replaced them by a concentrated area. Okay, and these ones are called booms. Okay, so all these are called booms. Okay, so area of the boom, so booms are concentrated areas. So area of booms, okay, which are concentrated areas, are equal to the area of the stringers at that location plus some part of area of the adjacent skin. Okay, right? What part? This we will talk in detail later. Okay, I'm just trying to explain thing in a in from the understanding point of view. The numerical things we will go into that later. Okay, so what? Let me reiterate what I'm trying to do. So I take these stringers, okay, which are thin wall beams, okay, which has a xy variation of the normal stresses. I replace them by the concentrated area at their location. So this, which are called booms. Now area of the booms is not the area of the stringer alone, but also some part of the area of the adjoining skin, right? Now that is one point, and the second point is that as soon as we approximate the stringers with this boom, we consider that the direct stresses in the boom is constant because it's a concentrated area. So in this stringer, the direct stresses are varying at different point of this stringer. Okay, so let me just enlarge and show it. So this stringer is something like this. So my sigma z is varying with x and y at different location of the stringer. But here I have only one sigma j, which is not a function of x and y because boom is a concentrated area. Okay, so that is, so the direct stress in the boom is constant. Okay, so of course these things will be much clearer when we actually get into example and solve it, but try to understand it from the philosophy of this idealization. Okay, so that is the second thing. So these are the two things about the boom. Now comes the skin. So in the actual structure shown in the figure 1, the skin has a certain thickness. Okay, but in the idealized or approximated structure, the skin has no thickness. It is zero thickness. Okay. Why? Because the area of the skin has been included in the boom. Okay. Therefore, we get rid of area of the skin in the idealized structure. So this skin is going to take only shear stresses and no normal stress, right? So in the idealized cross section, therefore, the skin has zero thickness and it is going to take only shear stress and no direct stresses. Okay, so if I want to summarize, in the idealized cross section, The booms are at the location of the stringer. They have a concentrated area. The area is equal to the area of the stringer plus some portion of the area of the adjoining skin. And there is no variation of direct stresses in the boom. So each boom has only one value of direct stress. And the boom is not going to take any shear stress. The shear stress will be carried or withstand alone by the skin. Okay, the skin is not going to take any direct stress, and the thickness of the skin is considered to be, is not, I shouldn't say zero, which is often confusing, is neglected. The thickness of the skin is neglected because it is not taking any direct stress. It is just taking the shear stress, which in turn can be called thought of as a shear flow. So let me then write down the main points of skin-stringer idealization. So to understand this, probably we need a discussion. It's very difficult to convey this whole idea through a monologue. I mean, I hope this is going to get much more clear as we discuss it during our discussion as well as when we solve problems. Okay, so but let me uh, write down or summarize the skin-stringer idealization. Okay, so the first point is that the stringers or any longitudinal members will resist only direct stresses due to bending. Okay. The second idealization is that the skin panel resists only shear stress. The shear stress is constant across the wall thickness. So the portion of the aircraft component or the portion of the skin between two stranger is going to have a constant shear stress. And also, as we have said earlier, much earlier, while analyzing shear stress in a thin wall beam, that the shear stress is going to be constant across the thickness of the wall, I mean wall thickness. And the third point is that transverse members are rigid in their own plane. So since they are rigid, they are not going to undergo any stress or strain, and we are not going to consider them in the stress analysis that we are going to do. Okay, so saying this, in the approximated cross section, so let me also summarize this. In the approximated or idealized cross section shown by figure 2, okay, A is stringers will be replaced okay. So with so these are the main points of approximated or idealized cross section shown by figure 2. Okay, so this of course will be discussed further with example, and I hope the concept will get clear through the discussions that we will have during the class hour. So thank you. So that's all for today's lecture.